Okay, so after the presentation, we're going to have a live Q&A with Tom. You can submit your questions at any time during this session using the Q&A box that you can see on the right-hand side of your screen. We're going to provide the attendees with downloadable copy of the slides near the end of today's session. And these slides will be available in the Handouts tab, also on the right-hand side of your screen, along with other helpful resources. And at the end of the session, I'll be announcing the 2 winners of this live session's giveaway. So with all that said, thank you so much for joining. And with that, I'll hand it off to Tom for the presentation.
Hello everyone, and welcome to my webinar titled Test Considerations for Harmonic Measurements of Passive Devices. My name is Tom Klinkenbeard, and I'm an applications engineer at Menlo Microsystems. Today I'll discuss how to create a test system with the sensitivity necessary to evaluate the harmonic distortion of passive devices or other components with very low harmonics. Before we start, I'd like to quickly thank our co-sponsor, RFMW. They are a distributor for Menlo Micro's RF switches and many other suppliers of RF components. RFMW has a worldwide distribution and technical design support network to help our customers with component selection, order fulfillment, and more. Moving on to the agenda for today, I'll start with a discussion of what harmonic distortion is and why it's necessary to test harmonic distortion on electrical components. From there, we'll talk about some of the challenges in creating a harmonic test system that has the sensitivity necessary to evaluate passive devices. Then we'll show a comparison of different test hardware and what the resulting sensitivity of the system is before finishing off with a question and answer session. Before we discuss the measurement techniques of harmonic distortion, it's a good idea to talk about the general principles of what that distortion is. Harmonic distortion is the generation of integer multiples of the principal frequency. In the graph on the right, you can see the principal frequency in blue and the second and third harmonics in red and yellow. Harmonic distortion is created by nonlinearities in the electrical circuit. And when discussing passive networks, common sources would be intermetallic effects when the electrical signal passes from one type of metal to another, oxidation of the metals in that electrical path, or damaged connectors, cables, and so on, among some other sources. Different sources can affect the odd or even harmonics more strongly. So a source that might attenuate the voltage peaks of a sine wave will affect the odd harmonics, while something that causes a faster rise time compared to fall time would create even harmonics. So why is it necessary to test harmonic distortion? Telecommunication equipment is often a driver for low harmonic distortion requirements of a system. This equipment requires low harmonic distortion to meet FCC guidelines for out-of-band noise. If a carrier RF signal is generating harmonic distortion in the system and that's broadcast out the antenna, the output power of the carrier signal must be lowered to keep that out-of-band noise below the FCC guidelines. Ultimately, the trade-off results in lower receive sensitivity and lower data rates for the wireless connection. Any test and measurement equipment that is used to test components that have these low harmonic distortion requirements must have even better performance than the device under test, because any harmonic distortion generated in the test system would mask the performance of the device under test. Each component in that test and measurement system should be verified for having low harmonic distortion. Now that we understand what we're measuring and why it's important to measure it, we can move on to the test system itself and some of the challenges you'll face creating a test system for very low harmonic distortion. A test system to measure very low harmonic distortion requires a high power input signal that itself has low harmonic distortion, filters with very high rejection for any of the generated harmonics in the system, reliable interconnects that themselves don't generate distortion before reaching the DUT, and potentially high performance switches for parallel testing of multiple DUTs. All of these requirements create a total harmonic distortion requirement for the test and measurement system that needs margin to the expected DUT performance to account for any kind of measurement accuracy. In our experience, this could be as much as 10 dB. The harmonic distortion of a passive device often requires a very high power input signal, usually generated by a power amplifier, though those power amplifiers themselves will have fairly poor harmonic performance. This can be in the range of 20 to 30 dBc, which would absolutely drown out the DUT harmonics generated that you're trying to measure. So to filter those out, often multiple filters are required to give enough rejection to leave room for the DUT harmonic distortion. In this case, a combination of a tunable bandpass filter and a low-pass filter is used to reach over 120 dBc rejection of the harmonics of the PA. Filtering is also required on the output coming from the DUT in order to separate the second and third harmonic from the principal frequency. This is necessary because a spectrum analyzer, which you would typically use to evaluate the second and third harmonic performance, will not have the dynamic range necessary to measure a very low power harmonic tone with a high power frequency at the input as well. For measuring the harmonics of a passive device, we recommend a diplexer to separate the principal frequency from the second and third harmonic. This is because it will not attenuate the second and third harmonics very much, while still having enough rejection of the high power principal frequency to give good sensitivity at the spectrum analyzer. We recommend avoiding reflective filters at the output of the DUT, which would reflect the high power tone, because that reflected power will go back through the DUT and could potentially generate elevated harmonics. The next challenge we'll discuss in designing a measurement system for harmonic distortion is the calibration. Both of the power at the input of the DUT of the principal frequency, as well as the power of the harmonic tones at the output of the DUT going towards the spectrum analyzer. We're using a power detector to monitor the power at the input of the DUT, but the losses of the coupler, the filters, and any cables and interconnects between the PA and the DUT all need to be measured, usually with a VNA, so that we know what the offset should be at the power detector to know the power at the DUT. At the output, we need to know the losses between the DUT and the spectrum analyzer so that we know what to adjust the measured tone power to in order to have an accurate measure of the harmonic power at the output of the DUT. If the filters are high loss, that can pose a challenge at the input because the PA power needs to be increased by more in order to compensate for that. Increasing the PA power might create additional harmonic distortion or just require a higher power and more expensive PA. At the output, any filter losses will reduce the sensitivity of the spectrum analyzer because the harmonic tones may be closer to the noise floor of your spectrum analyzer or the system in general. For this kind of system, it's very important to take repeated measurements of the system using something like a SMA adapter that typically will have very good and reliable harmonic distortion performance in order to understand the noise floor of your system and the measurement accuracy. In this case, we've made 100 measurements of a SMA female-to-female adapter in our test setup and shown some box and whisker charts of the second and third harmonic. You can see of the second harmonic, we are measuring a range close to 10 dB, plus or minus 4 dB roughly. And for the third harmonic, which is fairly close to the noise floor of the spectrum analyzer, we get a broader range due to the lower measurements being at the noise floor of the spectrum analyzer. This gives us a good idea of what the accuracy of the system is, and tells us that when we're measuring a DUT, in order to get the most accurate results, we may need to make repeated measurements if they are close to this noise floor. While less critical when making harmonics measurements of an active device like an amplifier, the cable choice can make a difference in a test setup when measuring devices with very good harmonic performance like a passive device. Our measurements showed that switching from flexible cables to a semi-rigid type of RF cable in between the filters and the DUT improved the harmonic performance of the overall system by more than 12 dB. The harmonics performance of each cable should be evaluated in your system when you need very high accuracy and sensitivity. Any damage to the insulation of a cable can increase harmonic distortion or cause other degraded RF performance of the overall system. So monitoring the cables themselves and periodically checking the insulation shielding and the interconnectors is often useful. In a sensitive measurement system, damage or debris inside the connectors can be a surprising cause of harmonic distortion in the system overall. Coaxial connectors can build up metal shavings from repeated mating and unmating that are then get stuck to the gasket, as you can see in the image on the top right. These metal shavings can actually generate harmonic distortion due to intermetallic effects in the path of the ground of the connector, and this will cause a deterioration in the harmonic measurements coming from that system, potentially changing over time as the connectors are mated and unmated. This kind of debris should be cleaned off of the connectors with a fine tip swab, or the connectors should be replaced if they're damaged in order to maintain the performance of the system. If the device under test is a surface mount device, it's often useful to mount it on a connectorized PCB when you're doing RF performance evaluation. In this case, it's important to select the right plating on the PCB if harmonic performance is one of the key specifications. Electroless nickel immersion gold plating, or ENIG, is a common plating for RF PCBs, but we found that it degraded harmonic performance of the PCB itself. Depending on the thickness of the nickel layer, we found that a calibration line on an ENIG PCB would have 30 to 40 dB worse harmonic distortion compared to a rigid SMA adapter in our test system. We recommend using nickel-free plating such as electroless palladium with either immersion or autocatalytic gold, EPIG and EPAG respectively. Another option known to have good harmonic performance would be a silver plating. We also evaluated several connector types, but we didn't see a measurable impact between different styles or materials of the connectors. Connectors with stainless steel and with brass bodies were both measured to have no significant difference in harmonic performance. Field replaceable connectors, such as the ones pictured, were compared to ones with soldered pins, and we saw similar results there as well. Lastly, we compared SMA type connectors versus 2.92 millimeter connectors, and we didn't see a harmonic performance change resulting from the different dimensions or the different dielectric material of those two types. In general, we would recommend selecting a connector for the reliability of the connection and for the frequency performance that you need to evaluate your harmonics at. Often, once you've designed a test system that meets your requirements, it later becomes necessary to increase the throughput of the test system. A harmonic test system capable of measuring low harmonic distortion requires expensive test equipment, so duplicating the setup is costly. Instead, you can add single-pole multi-throw switches to allow several DUTs to be tested sequentially. When combined with software automation to control the test equipment and handle the switching, throughput can be multiplied without having to duplicate the entire setup. Increasing throughput of your setup by adding switches is a good choice in a production environment for a few reasons. Decreasing the time it takes to do production testing directly reduces the costs of goods sold and lead times. However, choosing the correct switch for this application can be challenging. If we assume an input power of plus 35 dBm and look at the semiconductor switches with the best linearity on the market, they typically create harmonic distortion in the range of negative 100 dBc per switch, and most semiconductor switches will be closer to negative 80 dBc. That's equivalent to a harmonic tone with a power of negative 115 dBm, to put it in scalar terms. If you have multiple switches, that would further reduce the sensitivity of the test system, such as in the setup below. If the expected performance of the DUT is close to this or better, then it's recommended to choose either a coaxial relay or a MEMS relay, such as those offered by Menlo Micro. Between the two, MEMS switches have advantages over mechanical relays in faster switching time and higher reliability. The switching time of a MEMS relay will be measured in the microseconds instead of the milliseconds for a mechanical relay. And the reliability of a mechanical relay typically only reaches up to 1 million cycles, while a MEMS relay can reach into the billions of cycles. In the diagram below, you can see our example test system with added RF switches. This harmonic test system is capable of sequentially testing 4 DUTs and measuring very low harmonic distortion thanks to using Menlo Micro MEMS switches. Another reason to include switches in this kind of setup is to increase the test coverage of a single system. Being able to evaluate multiple DC and RF parameters with one test system saves time and cost when compared to having to insert the DUT into multiple test systems manually. Here we show a system diagram which allows testing DUT harmonics, now including additional paths that can lead to other test equipment. One option is to connect a source measure unit, or SMU, to allow the measuring of DC parametrics, such as resistance of the DUT or leakage current. A vector network analyzer, or VNA, can also be connected to allow measurements of broadband RF performance. In this case, choosing a MEMS switch is critical. Traditional RF semiconductor switches are unable to pass both DC and RF signals. Some specialized and expensive mechanical relays can, but even these will have a larger impact to high-frequency RF performance than a MEMS switch, in addition to the longer switching time and reliability concerns that we discussed previously. Now that we've discussed many of the design challenges of creating a harmonic test system, I'd like to finish this talk by showing a real-world example of the benchtop harmonic test system, which we use to evaluate the harmonic distortion figures in this webinar. Each piece of test equipment and RF module is labeled in the images here. I've also shown the signal path of the high-power RF tones at the principal frequency using red arrows, and the signal path of the harmonic tones using blue arrows. In this example, we show a RF shielding box, which we used during our evaluations to ensure our results could not be affected by any incident EM radiation in our electrical lab. But for most characterization and test systems for harmonics, such RF shielding isn't necessary. To start in the test system at the signal source, we use a signal generator connected to the input of a power amplifier, shown at the top of the image, in order to create our high power signal. That high power signal passes through a coupler with a power detector on the coupling port. We use this power detector to monitor the input power to the device under test. The output coupler is connected to the bandpass filter in order to filter out the harmonics of the PA, and then that bandpass filter, after passing through the RF shielding box, is connected to a low-pass filter to add further isolation to the PA harmonic tones. The output of that low-pass filter then connects to the input of our device under test. Here, that device under test is the calibration line of our evaluation board. The output of our device under test, now carrying both the high power RF tone and the harmonics that we're trying to measure, is connected through the RF shielding box and then to our diplexer. This diplexer splits the high power RF tone at the principal frequency in the red arrows and the harmonic tones, the blue arrows, into two different RF paths. The one output of the diplexer carrying the high power RF is connected to a 50 ohm high power load, while the other output of the diplexer carrying the harmonic tones we connect directly to our spectrum analyzer. We use that spectrum analyzer and move the center frequency to double and triple or so on for further harmonic tones, the frequency of the principal frequency. This last slide shows the test procedure we used in our evaluation. If you're creating a test system for harmonic distortion, all of the diagrams and the test procedure in the slide deck represent our recommendations for that system. By referencing this webinar, you can create a test system that can accurately measure harmonic distortion of passive RF devices with better than negative 130 dBc expected performance. Thank you for viewing this webinar by Menlo Micro, co-sponsored by RFMW. I will now open the floor to Q&A.
Okay, thanks, Tom, for that great presentation. We've already have several interesting questions lined up, but I want to let our audience know that there's still time to submit your questions. So please add them to the Q&A box if you'd like. Okay, Tom, are you ready to answer some questions?
I am, thank you, Jeff.
Great. Okay, first question is, what is the root cause of the 12 dB better performance of a single rigid cable?
That's a good question. So both cables we tested, they're both SMA, they have the same Teflon dielectric. So we believe that the primary contributor is the ground shielding around the cable. So the braided, semi-rigid shielding around the semi-rigid cable gives us better harmonic performance than the more flexible material in the cable itself, so not anything to do with the connector part of it.
Okay. Okay, next question. Talk about